Thank you. Yeah, it's nice to be in here for the presentation. Not the greatest weather coming down from Florida. Okay, so today I'll be talking about multi-scale X-in-the-loop simulations for aerospace applications. I'll briefly covering all the bases in terms of small scale to large scale hardware in the loop simulation for the hard real-time applications in aerospace domain. The purpose of my talk is to provide best-in-class real-time solutions that meet or exceed your mission critical requirements when it comes to aerospace applications, and also not to try being a real-time Linux evangelist during the talk. Okay. So let's begin with briefly covering real-time system design. So you have your real-time requirements specified in terms of the time loop. So you define your real-time. For this example, I have 1 millisecond loop. I have some algorithms to simulate. I have sensor inputs and actuator outputs. The first step you'd begin would be to simulate a few things, what you need. And then maybe when you are ready to prototype and test it further, you add your hardware in the loop, such as sensor inputs. For my case, I have a joystick or a camera, and then I send the signals out to the actuators. I further verify and validate my system before I eventually deploy. So in this talk, what I discuss should cover everything that comes before deployment. You simulate multiple times. You can prototype, test, and validate using actual hardware in the loop of your X. Okay, so what does that X mean? It depends on the context, what you want to achieve. So depending on the situation, you can have AI in the loop, you can have actual software in the loop, a human or a driver in the loop, whatever you like to call it. You can have your physical models in the loop, you can have processors in the loop, and full-fledged hardware in the loop. Okay. And by scale, I mean from very small, physical models to up to a massive scale space station. What kind of solution do you want? We have solutions available for all kind of simulation. We start with a very small dual core, TX2 like system up to 224 cores of CPUs. Okay, so let's break it down into different scales. First of all, if you talk about a very small scale application, your priorities can be portability. You want to do some kind of AI in space in like a small embedded box. You want to work with physical models or prototypes of your actual big system, such as nanosats are perfect example for this scenario. And the X here could be the AI or could be software in the loop. For that, we have partnership with NVIDIA, where we have different solutions ranging from your traditional Jetson boxes, including ruggedized systems by different vendors that work with us, and also solutions for autonomous driving. Obviously, these are standards, products that we support, but we also have custom support for many different kinds of embedded systems. So here's an example. I have a Simulink model of a drone. Okay, I deploy that drone in a small Jetson box. I control it with a joystick, and I connect to an image server, like an image generator. And here I can, simulate a very simple example that I use a joystick to run a real-time loop and visualize everything that is generated by the image server. And we have this demo set up at our table. I'm sure some of you have tried it. It's very simple. The only difference for the table demo and the example here is that the image is being generated in a virtual machine at our table. So we are capable of making virtual machines real time too, which we'll discuss later in the slides. The second scale is slightly bigger, but here your focus is customization. You need something like in a custom software-defined radio, scenarios such as space rovers, and you want high fidelity. So this is somewhat sort of processor in the loop simulation where you plug in some kind of controllers in the loop and provide more fidelity to your testing and verification. So X could be a human in the loop, an actual physical model in the loop, or processor in the loop, like I said. And how we solve it, we uh, manufacture our own FPGA board based on the Intel Aria, and these are highly programmable core FPGA boards with multiple IP cores, and you can use our FPGA workbench to simply drag and drop modules that you need. It's very simple. You don't need an FPGA engineer to customize the boards or write the HDL code, and you burn the firmware into the FPGA, and then you have your custom board that you can use to control any kind of control system, guidance, navigation, control system. So here's another example of this scale. Here you can see a classic example of inverted pendulum problem, right? So in this case, we used an FPGA to control the motors in the card that is balancing the pendulum based on random force acting on it. It will self-balance even with turbulences. If you touch the pendulum, it will just realign itself and you will just keep balancing itself. So it combines the classical control problem with the real-time loop and how we can do it with FPGA. So we simply send the signal to the angular encoder, and then the motor will provide the PWM out signal to balance the pendulum. Okay, so again, very simple example, but it can be extended to very large-scale problems like the rockets landing backwards on their thrusters. They are examples of classic inverted pendulum problem. And finally, if your necessity lies in extreme determinism, you want to do extremely heavy computations, you need signal conditioning for your large hardware in the loop simulation, uh, then that's the scale 3. And we have our standard offering, which we call as AeroHawk. It is the state-of-the-art, flexible, box fine-tuned with popular cards, I/O cards suitable for aerospace industry. We support AirInc, 1553, MFIO cards, MOXA, and they are available in 4 to 24 core processor systems. You can get a rack mount, which includes signal conditioning and everything for that. Okay, so for example, if you're simulating a jet engine, we can create a real-time turbine engine simulator using the AeroHawk. And in this picture on the right-hand side, you can see the location of AeroHawk mounted on the rack, and then we have also signal conditioning features embedded onto it. So this will help you simulate even large scale, a real jet engine with, if you want. We can also do like aviation, the wing flaps and the rudders and everything that can be plugged in, and everything is tightly knit, and you can run your simulation in your real-time time loop. And for the fault insertion and signal conditioning for large-scale, hardware in the loop simulation, we can perform signal conditioning, provide fault tolerance capabilities, and handle up to 1,600 signals, which is suitable for any large-scale simulation system. So right up till now, I've been talking about scales of different things. I'm showing you hardware offerings, how we can scale out. But how do we do that? How do we support the real-time stuff? So we have all kinds of considerations for the real-time scenario, and how we support it is we have our custom input-output, and we also manufacture our own cards at Pompano Beach, Florida. We support GPUs. We have our own real-time Linux. Some people could not believe it when we talked about it at our table. We also have a high-level real-time simulation framework. If you don't like to work at the operating system level, we provide a high-level tool with a GUI that can help you set up your simulations and run tests again and again without having a deep knowledge of the system. We also have tracing, tuning, and debugging tools for your real-time systems, specifically designed for real-time applications. And finally, one of our newest products, and we're very proud of it, we are able to make virtual machines real-time, so that now you can have one box, run multiple operating systems on it, keep them isolated, and directly pass specific I/O to specific virtual machines, and still be able to meet your real-time needs. So these are some of the concurrent input-output cards. That includes our programmable FPGA cards and multi-function cards. We also support off-the-shelf I/O, including AirInc 664, 429, 1553, and you name it. And if you have any other cards, we can test it and make them compatible. If you're concerned about running, deep learning on your system, so of making intelligent application, we support GPUs. We have partnership with NVIDIA, like I mentioned before, and it's interesting for you, but not for me. But our drivers, our engineers write custom drivers for NVIDIA, which are actually more optimized than standard NVIDIA drivers for real-time applications. So we do stuff better than them. And the core of our products is the Red Hawk Linux. I know that many of you use it, and some of you have already heard about it. We use standard Linux distributions and build enhancements on top of it to make it real time. We fine tune it so that it doesn't break. So if you have a preference for Red Hat or Ubuntu or CentOS, I mean rest in peace. So now we have Rocky Linux. So you can use all those distributions, and we can provide a layer, which is Red Hawk Linux, which is co-resident with your actual distribution. So you're still using a standard Linux, but you have real-time capabilities on top of it. And our high-level simulation framework, which is a simulation workbench, and it has standard support of many third-party vendors. In this diagram, you can see more of an automotive sector, but we also support many standard libraries and plug-in third-party things, and including MATLAB Simulink if you're a modeler. And it can support up to 224 CPU cores. So that large of a scale of simulation can be supported by just a high-level tool, including 3 terabytes of RAM. So that's pretty big. And our Nightstar suite is the debugging and tuning tools, especially the NightView source level debugger. It debugs your real-time application supports C, C++, and Ada. And also, you can analyze your whole system using Nitrace. You can create intuitive graphs about what's happening at the kernel level and the system level. Or you can target certain user applications to identify what events are happening. You can identify overruns and manage all your resources so that you're optimally running your real-time applications. And then to the Red Hawk KVM-RT. So it's a KVM-based virtual machine hypervisor. And it's a type 1 hypervisor, which means it runs on bare metal. So as you can see in this figure on your bottom right, you can see that virtual machine 2 has access to exactly 2 PCIe cards. It has dedicated 6 cores, and it's not interfering with the Windows VM in the purple, where you might be running something else and using a different card. They don't interfere with each other. They are essentially isolated and shielded completely so that no other interrupts, local timers or processes interrupt while the real-time application is running on a virtual machine. And this has been useful to a lot of customers who are unable to move away from the legacy systems. We have been able to provide them a virtual machine solution so that now they can use our KVM-RT product to maintain the real time, at the same time port all those really old software and hardware to a newer boxes. For example, Solaris, right? It's not supported anymore, but you can still run Solaris on one of our virtual machines and maintain your legacy real-time systems. Keep running that test, never stop. So here's an example. I'm not sure if the video is playing. Let me try to play that. So here in this example, this is an automotive example, but could be relevant to any ground vehicle. So here, the visualization is happening on Windows 10 machine, and the simulation is running on Simulation Workbench, which is running on top of Red Hat Linux. So as you can see, if someone is driving and doing a test run, they don't observe any lag in terms of their man-in-the-loop simulation in this case. A driver is actually driving a steering wheel and moving around the MCD, the Michigan Test Ground. Okay. So you can consolidate multiple systems, not just one, different variety of operating systems and software and hardware simulations, and then you run it on the single system. You don't need to manage multiple pieces of hardware for that. Yeah, our engineer made sure that it was funny. Okay. So yeah, we offer a complete ecosystem. You have a team of developers somewhere, a team of testing engineers somewhere. You do some kind of deep learning. You have a plant and a controller here for your GNC applications. You want to generate images for visual simulation. Have a server farm connected somewhere. Up until the data center level. We cover everything. So if you need any kind of solution that deals with real time, especially in aerospace domain that involves guidance, navigation, and control, speak to us. So that's why we are here for, and we will solve your problem. So this is the complete product suite. So at the end, I want to point out again, these are the standard offerings. Involving I/O cards to FPGAs to real-time Linux to image servers to debugging and tuning tools. But we also do custom solutions for customers who need like extremely specific solutions for their project. So the more we know your project, the better we can solve it. And we have solutions for every scale, like I summarized during this talk. So without taking further of your time, I can answer your question.